Hello students, let's understand weightlessness condition. Now what is weightlessness? It's a condition where a person inside the gravitational field does not experience the gravitational force. What I mean to say is the gravitational force is there but its influence is nullified. That is, the influence of gravity is zero. Let's understand this with an application. You will understand it better. Now let's consider weightlessness condition in a moving lift. Now before I go directly to this moving lift concept, let's understand the basics of what are the forces acting on this person standing on the platform. Now if he is stationary and standing, the first thing which comes to our mind is the weight, which is nothing but the gravitational force exerted by the earth, which is acting downwards, given as mg. Also, since he is in equilibrium, he is standing on the floor, then obviously there must be an equal and opposite force balancing this weight. That is nothing but the normal reaction acting on him, which is equal to the weight but acting in the upward direction as shown in the diagram. Now because of this normal reaction, he feels his weight. Okay, so if I consider him to be in equilibrium, then the forces which are acting on him are balanced. That is, if I consider the resultant force acting on this person, then definitely the resultant force acting on this person would be the weight minus the normal reaction, which will be obviously zero because he is in equilibrium. I hope you understood this very elementary condition. Now let's move on to the condition of weightlessness in the lift. For this, first consider a person who is standing inside a stationary lift. Now what are the forces acting on this person? Firstly, there's a weight which is acting in the downward direction, mg, and there's an equal and opposite normal reaction acting in the upward direction as shown in the diagram. So if I consider Fr as the resultant force, then the resultant force for this person would be the difference between mg and n, that is mg minus n. Now students, according to the Newton's second law, you know force is given as ma. So I can write the resultant force as mass into acceleration, where Fr is the resultant force, m is the mass of the person, a is the acceleration of the person. So if I substitute this Fr as ma in this main equation, I get ma is equal to mg minus n. Clear? If I just rearrange this and I take n on the other side, I get n is equal to mg minus ma. Or simplifying, I get n is equal to m into g minus a. Let's consider this as a general equation of normal reaction felt by that person. And a over here, a, that is the acceleration with which that person is going down when the lift starts moving down. So you can call it as acceleration of the lift or acceleration of the person, because both are going to go down finally in my later half of the explanation. So remember this equation, because on this mathematically I will try to explain you weightlessness. Now if I consider the lift to be initially stationary, so a is 0. If I substitute that, I get the normal reaction felt by the person as equal to mg, right? So in this case, if the person, example, if the person has got a mass of 10 kg and acceleration due to gravity is 10 meter per second square, then in that case the weight or the normal reaction felt by the person would be 10 into 10, that is 100 Newton. That means he feels the weight of 100 Newton. Let's consider this as the first condition, that is when the lift is stationary. Now we'll go to the second condition. Let's say now the lift is moving downwards. Okay, so let's start with the normal reaction acting on him. The normal reaction force over here is given as n is equal to m into g minus a. Mass of the person, let's say 10 kg, and a is the acceleration due to gravity, that is 10 meter per second square. Now consider the lift moving down with an acceleration given as 2 meter per second square downwards. Okay, so the lift is moving down with an acceleration of 2 meter per second square. So the normal reaction will now become 10 into 10 minus 2, that is 10 into 8, that is 80 Newton. So in this case, when the lift is moving down, that person feels a weight of 80 Newton. Earlier, when it was stationary, he was feeling a weight of more, 100 Newton. Now when the lift is moving down, he is feeling the weight less, that is 80 Newton. Now let's go to the final condition. If I say that the cable of that lift breaks, that is, the lift and the person is freely falling down, that is, the acceleration of the lift is same as the acceleration due to gravity. Okay, then in that case, if I start with the general equation of the normal reaction, the normal reaction in this case is m into g minus a. But the lift is moving down with an acceleration same as that of acceleration due to gravity. So if I substitute in place of a as g, I get m into g minus g, that is m into 0, that is the normal reaction is 0. It is because both man and lift are moving downwards with the same acceleration as that due to gravity. They are both freely falling down. So in this case, the feeling of the weight which that person gets is 0 Newton. And students, this feeling of no weight is nothing but called as weightlessness condition. So now students, consider me standing in a stationary lift. In this case, the normal reaction will be the same as the gravitational force experienced by me, which will be maximum. Now suppose if I consider the lift starts moving downwards. So I consider the lift moving down. As the lift starts moving down, then the normal reaction will decrease, right? So the influence of the gravitational force will decrease. Now suppose if the lift starts moving down even more faster, that means suppose if the lift starts moving with an acceleration same as the acceleration due to gravity. I'm considering the lift and myself to be like a freely falling body. So now let's increase the acceleration of the lift same as the acceleration due to gravity. Then in that case, I will start experiencing weightlessness. That is, the normal reaction will become 0, and this is called as the feeling of weightlessness. Okay, let's decrease the acceleration now. As I decrease the acceleration, I start feeling my weight again, and the normal reaction goes on increasing. And finally, if I stop the lift, the acceleration due to gravity is completely felt by me, or in that case, my normal reaction is same as the weight. Now, let's understand weightlessness condition in a satellite. Consider an astronaut of some mass inside a satellite which is moving with a constant speed along the circular orbit. So a satellite revolving inside the gravitational field of Earth, and one astronaut inside that satellite. Now that person inside the satellite, he's inside the gravitational field, but still inside the satellite he will experience weightlessness. To understand this, let's consider a satellite which is inside the gravitational field of the Earth and revolving in a circular path. Now, as a satellite is revolving in a circular orbit, there is a centripetal force, which is a gravitational force acting towards the center of the Earth, which is balanced by the centrifugal force, which is in the outward direction. So the gravitational force is there, but it is being nullified by the centrifugal force, because of which its influence becomes 0. That means both the satellite and the astronaut are attracted towards the center of the Earth. Okay, but there is a centrifugal force also which nullifies the effect. And here the gravitational acceleration is nothing but equal to the centripetal acceleration. The force exerted by the floor of that satellite on the astronaut becomes 0. That is, the normal reaction becomes 0. And this way, the person or the astronaut starts feeling weightlessness inside the satellite. It's just like a freely falling body or the weightlessness condition explained in the lift. So there is gravitational force, but its influence is not there, or its effect is being nullified by some other force because of which the person experiences weightlessness.